Right, hello guys. Today we want to work on a very peculiar issue with the vtable implementation in newCTFE, which causes it to sometimes not have the vtable. I know this sounds a bit crazy, but this is how it is. So there is a file which does demonstrate that, and that one is this. These function calls should produce a 2, 1, and a 10, and they return that in the order 1 to 10. When we execute that with an unmodified DMD, we get 1 to 10, as we should. As soon as we use the modified version that uses newCTFE to execute this, we also get 1 to 10. Right, so that seems to be correct. One would assume, however, if I change the order in which the function calls are being done, then suddenly we get a 0 where there should be a 2. And we also have an unused slot in the vtable, just as before, and what's worse is that we have an invalid function pointer inside the vtable. Right? So my assumption is that that invalid function pointer indeed is part of the vtable that comes after it. So this pointer is in reality the parent part of the vtable. Now I do have to have a way to visualize the vtable layout somehow. Let's do it like that. Let's do it textually. So first in the vtable at location 0 there is the vtable, the parent vtable, then 1 to n plus 1 are function indices. The function indices and n plus 1 is the end of the vtable. And the parent vtable is the start of vtable. Right? So if there is no space where the function pointer should be, so we didn't count that, and we counted and we put in the end of the vtable too soon, then for the next vtable here's parent pointer of next vtable, right? So we will be able to see that if we print the actual locations on the heap where the vtable is. And we can do that by modifying the dump vtable function. Dump dump vtables. And for each vtable, right here, it does emit the vtable index. But we can of course also emit the actual address this is at. And to get the actual address, we just have to print IDX. I believe that seems to be the actual heap address, and sure enough we get the value from the IDX. So this is the actual heap address of the thing. So we can write here add colon %d, and this is a second thing. So the value comes before the value. We write the index, and then we should see when we recompile that the vtable index is right, and where another one begins. Oh, we don't write that for the invalid function pointers, but all vtable pointers are integers, so they have the length of 4, which means if that here is at 184, then the 6 here is at 188, which is the place where this vtable says it starts, and it starts with its parent pointer, which is 132, which is exactly what we see here. So 132 is at this location because it is the vtable pointer of the following vtable, which means that we did not allocate enough vtable indices for this vtable. Yeah, this is kind of puzzling. This would suggest that either the vtable is not fully built, like the compiler itself will build the vtables lazily, which would make sense because building vtables is a bit expensive. Or we have some bug in our code, but that seems to be much more unlikely. I don't really know what to do about this. I guess what we can do is first off let's include the vtable index for the invalid functions. This would once and for all then verify that what I've just postulated is what actually happens. Gotta rebuild. There. So slow. Yes. We can now see that indeed it tries to find a function pointer where the parent pointer of the other vtable is, which means that the vtables are too short to keep all the pointers. Yeah. So that means when we build the vtables, we do not have all the parents. So alright. We go through all the classes, starting with the first, which should always be object. We get a pointer to the BC class type, and we get a pointer to the class declaration type. Right. Then we ask if this class has a parent index. If the class has a parent index, we get the BC class type out of here. We assert that the parent has the vtable pointer set, and we use that to set the parent vtable in our vtable. Then we go through all the functions and the parent. If we already have them in our vtable, we skip them. If not, we add that index to us. So we will always have at least as many indices as our parent. That's fine. Then we go through all used vtable indices that we have. If the vtable index is greater than the biggest one we have seen so far, we will increase the max index. And if the max index is greater than the vtable length, we will basically allocate more space for the vtable. So the vtable length would be max index plus 1. So the vtable entry is something we get from the class declaration inside DMD. We stick the vtable index in that we use. We get the function declaration out. We check that it is a function declaration, otherwise we freak out and assert. We get the function index and we store it in the vtable. So aside from one small inefficiency where we modify the length every time, which will allocate every time, but we go over it, there is no inherent problem with that. And let me, just because I happen to look at it right now, let me just make this a bit better. So now it will add 4 entries for every time it goes through there. And in theory we could even write this directly onto the heap, but I like to keep all modification of the shared execution state to be in a small block, because once we actually share this between threads, we have to make sure that all those writes and reads are synchronized, and for that, to prepare for that, we keep it in this small block here. There. Yeah, so there is no problem with the emission per se. I would say what the problem is when we add to the vtable calls, we do not add all indices to the used vtable indices, and we can easily check that. So there has to be a case where we break from here without adding the vtable index. And this could also easily be off by 1 error. I think no, it can't be, because the used vtable indices are added nonetheless. quite sure why we add the function here. We should only add the function when building the vtables. So let me see if that changes anything, because actually doing it here seems wrong. Used vtable idxs colon equals, that line's unique to that. So now if we build it, the result should be exactly the same than it was before. And it is. Also our other, just make sure that nothing else was broken by that, and our other vtable test also doesn't indicate any breakage. So yeah, this is fine. Now something seems to be wrong here. Which is that, oh, never mind. For some reason the 6th index comes before the 5th index, which is weird, but all the tests seem to pass, so that's that. I really don't know why we did the used vtable idxs. Why we did that? I have no idea why that happens. And also, in the add virtual call, there is nothing that happens that would change anything about that would change based on the order of calls. That wouldn't happen, because we assert that the vtable index is always there. It is never -1. So the only thing that could be there that would be order dependent is if a child could change the parent. If a child can change the parent vtable, and I guess it kind of has to, then we have an issue, because here we go through all parent vtables. Well, we don't go through all parent vtables, we go to our parent's vtable. However, if our parent hasn't been processed by this, or rather, if our parent or their parent hasn't been processed by this before we got processed, then we will not catch all used vtable indices when we do that. That is a very real danger. And what it means is that what we could do is do that loop twice, which is a quadratic loop. Do that twice. And in theory we would have to have it even more often than twice. We have to do it n times. So doing a quadratic loop, an on squared loop n times, means that it is actually a cubed loop, but since the class count should never be really high, we can probably do it. And I really have no better idea than that. So I'd say we do a cubed loop through over all the vtable indices, right? We do that here. And in theory we could do an early exit if we see that no changes have been done to the vtable indices. We could do that, but for now let's do the easy route. So we do that. And this complete outer loop thing here is done in here. Or we could force the parent to be processed first. Let's not do that. Let's do the thing which I said to do before, which means that as long if in one complete loop no modification occurred, we don't have to loop anymore. There is one space to correct the formatting. So now, if I do this class count times for each, we don't care which index we get, 0 to shared, newCTFE state, class counts. So if we do that multiple times, then we will get to a point where no modification can occur anymore. And if that happens, so just to check that we can produce it with the current broken version we have, yes. So we now change the code to run through all the vtables multiple times and hope we reach a fixed point. We can break when we reach a fixed point as an optimization. I'll do that later. But right now, if I'm correct with my assumption, the new version of the compiler should not emit, should not have this, but a correct vtable pointer instead. And we get a range violation. Let's see why that would be the case. Right. This whole thing only happens if there is a parent index. Which is why it was indented one more. But adding indentation is easier than removing it because there is a tab key for that. There we go. So yeah, we can only iterate over the parent field when the thing actually has a parent. And this should make sure we build the whole vtable for everything. Alright, this did not seem to help. We still have the invalid function pointers. The vtables are still too short. Which is strange, right? Because at this point, ct.used vtable idxs should contain all used vtable entries. Right? Maybe the issue is that we don't go both ways. That could be an issue. So, a child can get a used vtable index from the parent, but at the same time, the parent needs to be able to get a used vtable index from the child, right? If this relationship goes both ways, then the parents and the children, they will always contain the maximal length vtable, right? Not quite sure if that's a good idea, but that's the only one I can come up with, right? So this, doing the quadratic loop over that, did not work. But yes. What this would do is concentrate the whole inheritance hierarchy in the parent, which I guess is what we have to do anyway, because otherwise we do not allocate. No, actually no, we don't have to do this. Well, but that could be one thing where the order would be used. So I guess what we want to do is, we want to concatenate the vtable indices of the parent and the child, sort them, after sorting them, deduplicate them, and after deduplicating them, setting them to both the parent and the child is what I think we want to do. I'll be taking a break. After that, I'll be implementing a merge sort and a unique function, and then this problem will hopefully be fixed, but that I will show in another video.